Memory management on embedded systems is very different to if you have a big fancy operating system like Windows, Mac, or Linux. You have to be very, very careful about the allocations you make and even the allocation strategies that you use. We can't just go malloc and free this whole thing. Because in most circumstances, you are very constrained on time, CPU resources, and even the amount of RAM that you have. Today, we're going to explore a bunch of memory techniques that embedded system engineers use to keep their programs performant and efficient and, most importantly, deterministic. And we're going to demo it on this little guy right here. Now what we have here is a very simple program. If you can't understand this, it might be time to go back to class. Literally all we are doing is allocating space for 64 8-bit integers, and then we are filling them out in ASCII character order, and you can see the printout of that result right here. Now the first thing to note about programming on an operating system versus programming bare metal is that when we call malloc, we're going to get a virtual memory address. You might assume that when you call malloc, you're getting a real portion of your computer's memory. And you are, in a way, but it's kind of abstracted from you by your operating system. You get what's called a virtual memory address. So have you ever wondered why in your program, when you're using it, it seems like all of the memory start at 0? Well, that's because through the operating system, it's letting you do that, basically. And that's how we can get like predictable pointers and be able to do pointer arithmetic, because the OS is giving you predictable memory addresses. Because believe it or not, when you call something like malloc and the operating system allocates physical memory, it's not always in contiguous chunks, even though it's of great benefit to your program to assume like it is. So by providing you virtual addresses, you can actually do pointer arithmetic with memory, even if in reality it's kind of fragmented and not necessarily contiguous. Now incidentally, that actually does not really become a problem for us when we're programming bare metal on something like this. It's an abstraction needed by operating systems because you have multiple programs trying to do memory allocation all at one time, sometimes in parallel. And so in that case, you have multiple applications competing for physical memory, whereas with one of these guys, you only have one application competing for physical memory, and that is yours, buddy. So when we program bare metal, we don't actually use virtual memory addresses, we can use the physical memory on this chip directly, and that is actually really cool. A major mindset change you need to go through when you come from Linux programming over to embedded programming is that we generally always prefer to use static allocations instead of dynamic for a number of reasons that we'll explore later on. If your teacher or professor has gotten it into your head that globals are evil and you should never use them, this is another thing you have to unlearn when you come over to embedded, and there are strategies that we can do to make this pattern a little bit more usable. So for example, we can mark variables as static, or we can simply just not extern them, and you can see here that I've flipped this from a G to an M to indicate that this is a file private member. Now here's a pattern you may not have seen before, but is actually very common in embedded code bases as well. This is marking a variable as static inside of a function body. What in tarnation does that do, I hear you ask? What it does is it creates a globally private variable for this function. What this means is that instead of being placed on the function stack and therefore losing its value when the function exits, this actually gets a position in the data segment of the program provided you give it an initializer like this. The benefit of that is that subsequent calls to this function have a consistent state of this variable, it's globally retained, but other functions can't access it. And here we go, this little guy is going through and cycling through all the ASCII characters. How is that possible? How is it? Because if you look at what this program is doing, we are declaring this in a function. How is it possible that subsequent calls keep doing this increment? Well, it's specifically because we put this static thing here, and that is why we are able to get this constant state for that function, and this is a pattern that you see everywhere in embedded code bases. Despite what my clickbait thumbnail suggests, malloc is not an operating system call, it's actually a C library call, and so you can get it to work on some embedded platforms with a little bit of setup. What we're doing right here is targeting an ARM CPU, and for example what we need to do with ARM's newlib implementation is define an _sbrk function where we can essentially say if we can define a portion of physical memory to use as our heap, and define a function that can increment pointers according to a size within that heap, then malloc in the library can kind of take care of the rest for us. And in fact, if you're using STM32CubeMX, it is actually kind enough to generate this function for us. Another reason why embedded programmers generally don't like to use the malloc and free pattern is because it can be very unpredictable. In embedded, we have to deal with a myriad of different CPU architectures on a myriad of different microcontrollers with some different compilers, etc., and the implementation of malloc is completely up to the C library that you're using for your platform, and this is actually more important than you may realize. So consider that sbrk function that we just covered. Literally all that does is takes a range and just increments a pointer until it gets to that range after every allocation. Now you might expect after you call free a whole bunch of times on a bunch of random objects that heap is going to defragment itself. Well, guess what? It may not always do that, and in fact on many embedded platforms it does not do that explicitly. So you are going to be left with a whole bunch of memory fragmentation if you use a standard malloc and free pattern, and this may cause your allocations to fail in some cases. But that's not good enough, Hoff, I hear you say. I'm constrained on memory, and I don't actually know how many of each object I'm going to need at compile time. Can I still avoid using malloc on my bare metal system? The answer is yes. Here's a happy compromise pattern we can use with a couple of trade-offs. This is actually called a bump allocator. It's actually much easier to explain this one graphically. You can imagine this big white box as a contiguous portion of 2 kilobyte memory that we've allocated. That sounds really fancy, but on bare metal, it is literally as simple as doing uint8t buffer 2 kilobytes. That's it, because we're using real physical memory here. That's going to grab 2 kilobytes of real SRAM for us. Now, what we've got here in the blue is the start pointer and the end pointer, and the red is our current position pointer. So we've got this generic 2 kilobyte buffer. Let's say I want to allocate some objects onto it. I can allocate an object of one size, and it'll just move that position over here. So now I've allocated one object. I want to allocate another object, it just moves that pointer over here. Let's say I want to allocate a really small object, well, it's not going to move it very far, and I can allocate a really big object, and it's going to push it all the way over here, until we get to this end pointer, of which the application should refuse to allocate any more memory. And this is deterministic because it's literally just moving this pointer by a certain size. And the implementation of this is dead simple, guys. I've just defined a data structure container over here with the start, end, and position pointers. Then you can see to destroy the arena, all you do is you move the position back to the start, and to bump or allocate something, all you have to do is take in a size, do a little bit of alignment maths, and then you literally just do dhpos plus equal to size, and you return the size of that at the entry to the function. It's really, really easy. So how is this any better than malloc and free? In fact, if you've been paying attention, you had noticed that the thing that I just described is very, very similar to how the sbrk function that underlies malloc on this particular platform is working. Well, it's simply to do with the deallocation strategy. With a malloc and free pattern, you free individual objects, whereas with the bump allocator that we've been describing, you free the entire thing at once. So whatever is in that buffer, it all gets thrown away. You have no concept of individual object lifetimes. And Casey Muratori has a very interesting video where he talked about becoming an N+1 programmer, which kind of shows the progression where you level up to thinking about objects grouped lifetimes instead of individual objects and their individual lifetimes. It's very interesting. I recommend checking it out. To prove this crazy allocation strategy actually works, I've gone ahead and allocated a whole bunch of arbitrary objects just for this demo. So you can see here I'm grabbing 4 awesome structs, which are simply an integer, 40 characters, and a float. I've got 48 uint32s that I've just assigned right here. I've got 3 awesome vectors, well, sorry, epic vectors right here, which are just floats of x, y, and z. And then here you can see I'm calculating the Fibonacci sequence using dynamic programming on that vector that we just allocated. Then I'm going ahead and filling out my awesome structs with some random stuff, and then I fill out my vectors and I'm doing all of this printing thing. So literally what I'm just trying to demo to you is going from a completely arbitrary just set of bytes, and we can get all of these useful objects where we can actually do stuff with. Bada bing, bada boom, and you can see we print out. We've got our little Fibonacci over here. Let me just maximize that. We got our little Fibonacci over here. We've got the struct assignments we did. I was just assigning like A. We've got our vectors printed out, and at the end of the program, I actually demo to you just completely exhausting the rest of the heap. So after all of these allocations, we have 600 bytes left over, which we can do in 75 8-bit aligned allocations. If you're not sure about memory alignment, I do have a video where I cover this kind of thing. Then I destroy the arena, so I completely reset that pointer all the way to 0, so that just deallocates all of those objects in one go, and then I exhaust it again, and you can see we've got the remaining 1024 bytes left. This brings us to our final technique of the day, which is memory pools. This technique is so legit, there's even a Wikipedia page about it. The basic idea is that you split up your big chunk of memory into little smaller chunks or blocks, and you can just hand them out whenever your program wants to make an allocation. Now you might be wondering, Hoff, how does that solve any of the problems that we have with malloc and free? The answer is very simple. Because with malloc and free, you can allocate variably sized memory chunks, you can experience fragmentation once you go and free a whole bunch of those up, and we're going to demo that in just a second. So when you would imagine if you interlace big allocations with small allocations, you go big, small, big, small, and then you go free all the small ones. Now, you may have enough memory in total to allocate a big one, but you can't actually do that with malloc and free because your memory is severely fragmented. There's not enough contiguous space to allocate a big object. Now, this sounds great and all, but you may have realized what the major drawback of this method is, which is that even if you need to make a small allocation, it's going to hand you a block of memory that is the size of the chunk. It's a static sized chunk. So what that means, let's say I have my chunks in 64 bytes and I want to allocate something that's size 12 bytes. Well, it's going to hand me 64 bytes in total. Now, where you might want to use a technique like this, because this is an intentional trade-off, guys. And like I've been saying throughout this whole video, all of the use of these techniques is very, very situational on your embedded device. An example of somewhere where this technique may be useful that doesn't matter so much is if you have a lot of different objects that are very similarly sized, and so the extra memory you waste here and there with your block allocation doesn't really matter that much. It's more important that you don't get fragmented. Now, the implementation of this is not as complicated as you might think. We've had to expand our dumb heap just a little bit. The first thing you'll notice is that I've typedefed a new struct up here, which contains a pointer to the next block in the sequence. Because basically, if you go back to our memory pool thing, what all of these data have to do is reference the next free block in the list. This is what's known as a free list, and it's very important for our structure to be able to keep track of which blocks and chunks it's handed out and which are ready to go. And this is how we get our really fast allocation time, because it's just a pointer lookup as you would do with a linked list. And you can really see how simple that is with the implementation of the alloc and the free, which is what you're going to be calling during the lifetime of your program. Literally, all it does is it grabs the head of the free list, it sets the head of the free list to the next thing in the free list, and then it returns the previous head. Now, for the free one, wow, I've said free a lot of times in the last 30 seconds, literally all we're doing is prepending the block that the user wants to free to the start of the free list. And that is it. You might have noticed I also added this block T pointer into our dumb heap data structure, and that is simply so that we can keep the API consistent with the bump allocator. Let's get to the elephant in the room, which is this pool init function. I know it looks really scary, but trust me, we're just going to break it down. It's going to be fine. So think about conceptually how this memory pool works. You can imagine this whole big segment here as one big statically allocated buffer that we can allocate during compile time. Now, our job is to pick a size and split it up into segments. How can we do that? We can do that with pointer arithmetic because the user is going to provide us the size of the blocks that they want at init time in case they actually want to use multiple memory pools throughout their program for various different sizes and classes of objects. Knowing that theory, let's dig into the body of this function. The first thing you'll notice is that I have asserted we are given a memory aligned pointer as the backing buffer. And the reason for that is because whatever blocks we give to the user, we want them to be able to just cast that to an arbitrary object. And so we have to ensure that the memory that we give them is properly aligned, just like malloc would do. And so that's the assertion we make right up front. Now, this is the thing where we do a little bit of alignment maths. So if the block size is not properly aligned, we're just going to round it to the nearest alignment. And then the free list is going to be the actual beginning pointer of our backing buffer. So if you think about our backing buffer when we're splitting it up, the very first start of that is going to be the very first block that we're going to allow the user to allocate. Now, based on the things that the user has given us, like the end pointer and the start pointer of their backing buffer and the block size, we can actually go ahead and calculate the number of segments that we're going to be able to split that backing buffer into. And you'll notice that we return that right at the end so that the user can deterministically know when they're going to fail allocations. This is really important because you don't get that determinism with malloc. With malloc, you can free a whole bunch of stuff and theoretically have enough memory to do a big allocation, but then that big allocation can fail because it's fragmented. Here, we deterministically know the exact number of allocations we're going to be able to do before we've exhausted our resource. Now in the middle here is where we're just doing a little bit of pointer maths, so we're grabbing a pointer which is equal to the start of our backing buffer plus I times the block size. And if you think about it, that makes sense. If you want to grab the nth block, that's the calculation you have to do. And we are simply setting the next one to the I plus 1 of that, and that's safe to do because we're looping 2 segments minus 1. After that little bit of initial setup that you can run right at your microcontroller's start, you get very, very cheap and very deterministic allocations. It's actually a really, really nice strategy. Now the demo I cooked up to show you all is actually very simple. Literally all we do is we interleave big and small allocations and then free all of the small ones at the end so that we actually artificially create a fragmented heap. Then we do the exact same strategy with the pool, and we're going to see which one fragments and which one doesn't. So let's go ahead and give this a little program. And you can see immediately the results are that our heap strategy failed to do the allocation, but our memory pool succeeded. And this is exactly the determinism that a memory pool gets you, and it's up to you, the application designer, to decide if the potential of extra wasted usage on every allocation is worth that trade-off or not. I want to thank you guys so much for checking this video out, and especially for watching till the end. I hope this video has dispelled any fears that me getting a job at Microsoft is going to lead to the end of low-level content on this channel. It is literally just the beginning. I want you guys to relax. Thanks again. See ya.